So this lesson's really a neat one. It's about approximating integrals using power series. And the reality is, there's one background skill that we need. I need to make sure that you guys remember the alternating series form of the error, right? So the alternating series form of the error. And what that is to say is, suppose you have an alternating series. Suppose you've got, 1 minus a half plus a third minus a fourth plus a fifth, and so on. And let's say you know this is equal to something, right? The question is, what happens if you decide to only add up the first four terms? How far off is the sum of the first four terms from the actual infinite sum? And the way that we would write that is we might write, what is the absolute value of s minus, s sub 4, the sum of the first four terms? And the reality is that we know that this has to be less than or equal to the next term in line. We might refer to that as, say A5, the fifth term. So my error will be less than or equal to the next term in line, 1/5, right? The alternating series form of the error was a pretty easy thing. I'm really, really hoping that we remember that pretty well, because we will need that for this lesson. So the new problem that I want us to look at is this one. I want us to approximate the value of this integral with an error less than 0.01. And I'm pretty sure that I've done my job well here. I don't think that's an integral we can do by hand. If I had made this a normal x, just cosine x, then I think we can do this by tabular integration. But as it stands, we're stuck. I don't think this is really something that we can easily do. I might have just thought of a way to do it, but it doesn't matter. Another way we could go about this problem, especially if we want to approximate, is we can use a power series, right? Could we come up with a power series for x squared cosine squared of x? And if you're watching this at home, I'd recommend you pause the video, make sure that you can find the power series for that thing, and then come back to the problem. So I'm going to sort of step over to the side and do that. First, I want to remind myself what cosine x is. Cosine x is an even function, so it's all the even powers of x. That would be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and so on. So that means the cosine of the square root of x means I'll plug in the square root of x to all these places. 1 minus x over 2 factorial plus x squared over 4 factorial minus x cubed over 6 factorial, and so on. And then when I go back and do x squared cosine squared of x, I'll have x squared minus x cubed over 2 factorial plus x to the 4th over 4 factorial minus x to the 5th over 6 factorial, and so on. And the whole idea is I can use this power series to replace this thing, right? Now, this power series only works on the interval of convergence, right? So what is the interval of convergence of this thing? It turns out we can always use the interval of convergence of the function this was originally related to. So because this was based off the cosine x function, which has an infinite interval of convergence, this will also have an infinite interval of convergence. So I'm going to take this integral, and I'm just going to replace it with a power series. I now have the integral from 0 to 1 of x squared minus x cubed over 2 factorial plus x to the 4th over 4 factorial minus x to the 5th over 6 factorial, and so on. And so now I just evaluate this thing, right? This will be the 1/3 x cubed minus, let's see, and I'm going to start converting these factorials into actual numbers. This will be 1 over 8 x to the 4th. That's a 4th power from that and a 2 from here. The next one will be plus, let's see here, we'll have 1 over 5 times 24 x to the 5th minus 1 over 6 times 720 x to the 6th, and so on. And I'm evaluating between 0 and 1. And this is really where the magic happens. Because my bottom bound is 0, and I was centered at 0, all of these terms are going to disappear. So I'll plug in 1 for the top and get 1/3 minus 1/8 plus 1 over 120 minus 1 over 6 times 720 is 4,320, I think. 4,200, yeah, 4,320, and so on. So it'll be all that minus 0, right? And what I want, is I want to be able to express this thing as, I want my error to be less than, I think we said in the problem that we wanted it to be less than 0.01. Well, we're in luck. This thing is an alternating series, so I just have to keep going until I find a term that's less than 0.1, less than 1/100th. This guy right here is less than 1/100th, so the approximation phi integral requires only that I add up these first two things. 1/3 minus 1/8. Let's see here, I guess we could get a common denominator. That'd be 8/24 minus 3/24. So 5/24 is my approximation for that previously impossible definite integral. Keep in mind, this trick really only works well if your integral yields an alternating series. Because if we didn't have the alternating series form of the error, like where we could just look for the first term that was small enough, we'd have to rely on Lagrange, which is just a mess because you actually have to know about, the n plus 1th derivative. So when you've got an integral that yields an alternating series, it can be a really, really great way of approximating an integral. That's all I had in this video. I will see you in the next one.